Okay, guys, welcome to this first video. This first video is going to be about energy. So, I guess I should first start off with the definition of energy. This definition it's honestly not that important, but energy is defined as an object's ability to do work. You'll learn more about what work is in some future videos that I haven't made yet and probably shouldn't just stop procrastinating about. I'm getting off topic. Anyway. There are three major types of energy when it comes to physics, or at least so far, this is what we've learned in Unit 3. So, first we have kinetic energy, usually represented as K, and kinetic energy is equal to 1/2 times the mass times the velocity squared. Now, as you can probably guess from this velocity squared, kinetic energy comes from an object's motion, and the higher the object's velocity, then the greater the kinetic energy. Another type of energy is called gravitational potential energy, and it comes from an object's position in a gravitational field. Now, the equation for this is a little more straightforward. For some reason, it's referred to as U underscore G. I don't know why it is, but this one's pretty simple. It is just mgh, where mass is m, g is the strength of the gravitational field, or acceleration due to gravity, if you want to think about that, and h is just the height that an object is above, like, for example, the Earth's, like, yeah, the Earth's surface. So, like, for example, if I had an object that was 10 meters above the Earth's surface, then I could calculate the potential gravitational energy by doing mgh. I have ug is equal to, I guess I'll say this is 2 kilograms, is equal to 2 kilograms times 9.8 meters per second squared, as that is the acceleration due to gravity on Earth, times the 10 meters. And if you do this math, I mean, let's see, we have ug is equal to 2 kilograms times 98 meters squared, seconds squared. That is 196. And the units for energy are joules, J. Joules can also be represented as different ways. They can be Newton meters, or just Newton times meters. For example, if I was to break down this kg m squared s squared, I have kg m squared seconds squared. This I can convert to kilogram mass, no, not mass, meters, over seconds squared times meters. This whole thing is just Newton. That's a Newton meter. And as you could probably guess from this original equation, joules can also be represented as kilograms meter squared second squared. It's a little more complicated, but you do encounter it occasionally, so it's important to just remember. A joule, by the way, is the amount of energy, 1 newton, required to move an object 1 meter. The last type of energy that is important for Unit 3 is energy that is stored in a spring when it is compressed or extended from its equilibrium position. This is represented by US. Some people represent it as USPR for spring. But the equation for this is 1/2 K, where the K is the spring's spring constant, which, as you may remember, has units newtons per meter, times x squared, where x is the displacement of the spring from its equilibrium position. These are our three major types of energy, and sometimes people will sum up the energy. So I have sum of E. This is just going to be equal to K plus UG plus U spring. There can also be a differential to be made. This could be E naught. That would be K naught plus UG naught plus US naught. And E final, for example, that would just be this original thing. Now I guess let's work on some practice problems here. Okay. Let's say I have an object, a 2 kilogram object, so 2 kilograms, and let's say it is moving at a constant 5 meters per second. How would you calculate the object's, let's say, kinetic energy? Remember, constant velocity. What is the object's kinetic energy? Well, if you may remember, kinetic energy is equal to 1/2 mv squared. And at this point, I can really just substitute in my values. I have k is equal to 1/2 times 2 kilograms times 5 meters per second squared. These twos cancel out. I just have k is equal to 25 kilogram meters squared per second squared. And as you may remember, that is just a joule. So the kinetic energy of an object that has 2 kilograms of mass and is moving at a constant 5 meters per second will have kinetic energy of 25 joules. Let's do another one. Maybe this time let's do gravitational potential this time. Let's say I have, and let's do a 3 kilogram object this time. It's a 3 kilogram object. It is above a planet's surface, but we don't know the gravitational field strength of this planet's surface. What am I talking about? Let's say that this object is 15 meters above the ground, and let's say that it has a potential gravitational energy of 90 joules. How would you go about calculating the gravitational field strength from this information? All right, I'm going to assume you have given it a shot. So in this case, we have UG, if you may remember, and GH. We have our M, we have our UG, we also have our H, we don't have our G. So we could divide everything by MH, and we could get that G is equal to potential gravitational over MH. And at this point, I can start just chugging in my numbers. G is equal to 90 joules over, let's see, 3 kilograms times 15 meters. This is 90 over 45 joules over kilogram meters. So then I'm going to bring this over here. So now G is equal to 2 joules over kilogram meter. That simplifies to 2 meters per second squared. It's a little in the way. Hold on. There we go. That's a little better. G is equal to 2 meters per second squared. Let's do one more. This time, let's do the spring energy. Let's say I have a spring with a constant of, let's say this is a pretty tough spring, 500 newtons per meter. I don't know if that's tough or not. I'm just making up numbers at this point. Let's say that it is stretched 20 centimeters past its equilibrium position. How much potential spring energy is stored in this spring right now? Okay, let's say you've given it a shot here. We know that the potential energy stored in a spring is 1/2 kx squared. However, it's important to note that this x here, it needs to be in meters, because else the units won't actually cancel out. Meaning we need to convert this 20 centimeters into meters. 20 centimeters, if you divide that by 100, you just get 0.2 meters. And boom, now we have our displacement in meters, and we can just start throwing in our numbers. Potential spring energy, 1/2 times 500 newtons per meter times 0.2 meters squared. That is 1/2 times 500 newtons per meter times 0.04 meters squared. Let's see how this simplifies. I can simplify that down to 250. I'm going to rewrite that as, let's rewrite it as 4 over 100. This should make it so my brain can process this. 25 and 10, if that's 5 and 2, that cancels out, and that's 5. So it looks like our stored spring energy is just 10 joules. Yeah. Okay, now I feel like I have to check if it's 10 joules real quick. Desmos. That is not. Hold on. Give me a sec. 1/2 times 500 times 0.2 squared. It is just 10. I did my math correctly. Yay! Alright, I think that should be enough for this video on energy. Next up, I will have a video on systems. Hope to see you there.